Welcome back to the Mechanics of Solids lecture series. We're working on internal shear and moment functions in beams. In this video, we'll continue the example we started in the last video by solving for internal shear and moment functions. Notice that we've recorded the support reactions that we found in the last video. Remember that we start by dividing the beam into regions separated by load discontinuities or changes in the load functions. For this beam, we have region 1 to the left of point B, and then where this distributed load starts, we have to start a new region. So region 2 to the right of point B, or where the distributed load acts over the end of the beam. As we solve for these moment functions, I don't mind if you drop the units, as long as we recognize that the working units are kips and feet. So shear force in kips, and moments in kip feet. To analyze the shear and moment functions in each region, we need to analyze a free body diagram. We'll start with region 1, make a cut somewhere in the middle of that region, and draw a free body diagram of the beam to the left of the cut. On our free body diagram, we'll add in any loads or reactions to the left of the cut. In this case, we only have the concentrated moment of 120 kip feet. The distance along the beam is x, which represents anywhere between A and B. And then at the location of the cut, we'll draw in the unknown shear and the unknown moment, both in the assumed positive direction. To solve for the shear function, take sum of the forces in y equal to 0. We have negative v of x equal to 0 since there are no other forces in the y direction acting on this region of the beam. To find the moment function, we'll take sum of the moments at x equals 0, positive in the counterclockwise direction. And remember, it's important to sum the moments at the location of the cut for convenience and simplicity. So we have the moment at x acting in the counterclockwise direction, plus the concentrated moment at the end of the beam, which we'll just represent as 120. It's not multiplied over any distance because it's a concentrated moment. Set that equal to 0, and we find that m of x equals negative 120. Now let's analyze region 2. We make a cut somewhere in the middle of region 2, draw a free body diagram to the left of the cut. Note that this is not lined up with my sketch above. Add in any known support reactions or loads. So we have a 120 kip feet concentrated moment at the end. Somewhere over here, assumed point B, we have the distributed load of 5 kip per feet acting to the right of point B. Let's denote the distances. Distance from A to B being equal to 8 feet. And since the total distance to the location of my cut is x, this distance right here will be x minus 8. Finally, draw in the unknown internal shear and moment, both assumed to be in the positive direction according to our sign convention for internal shear. So we solve for V by taking the sum of the forces in y equal to 0. We have negative v of x minus 5, the distributed load, times the distance, x minus 8, over which it acts. Set that equal to 0, and we find that v of x equals negative 5 times x minus 8. Assumed units are in kips. To find the moment function, m of x, we take sum of the moments at x equal to 0. It starts off very similarly to region 1. We have m of x plus 120. But finally, in this region of the beam, we also have a contribution due to the distributed load, which I will represent as the value of the distributed load, 5, times the distance over which it acts, x minus 8 squared, and then divided by 2, which was explained in one of the previous videos. Set that equal to 0. M of x equals negative 120 minus 5 halves times x minus 8 squared. And for drawing the moment diagram, it's actually convenient to leave it in this form. So we'll go ahead and conclude this example in the next video.